If you don't mind, I think you can hold off on homework questions till review time. We've got to get through these two sections first. So we were in 9.1, looking at, the last example we looked at was verifying solutions to the initial value problem. And so now what we want to look at is how we find general solutions to a differential equation such as this. And then we'll look at initial value, a couple of initial value problems. Okay. So I hope these are very straightforward. I mean, they're basically the most simple kind of differential equation you could possibly solve, where we're actually just given the derivative as a function of t or x or whatever, and we're asked to find the general solutions. In other words, we're after what y of t is. So y of t would be given to us by taking the antiderivative of the derivative. So that's all we need to do here is just find the antiderivative of 12t to the 5th minus 20t to the 4th plus 2 minus 6t to the negative 2. Okay, so that's a pretty basic one, but still illustrates the idea. Find the function of, given a derivative, we utilize the antiderivative. So we have what, 3t to the 4th, or sorry, nope. 2t to the 6th. We're going to have t to the 5th, 20 over 5. Plus 2t. Then we have antiderivative here is t to the negative 1 over 6 over negative 1, so plus 6t to the negative 1 plus c. And since that's the only antiderivative we have to compute, we'll call that c. If we're given, like in the second problem, second derivative, we'll have two constants. So at that point, maybe we would label our first constant as c1 and then the next one as c2. But that is our general solution. And the only thing that really differs is when you're given initial conditions, is then we use the initial conditions on y of t to determine what that constant actually is. So are there any questions on that? Okay, so example 2, we're given the second derivative, so we want to take two antiderivatives. Let's see if we can get the answer. Y prime is the antiderivative of y double prime. So we have e to the 3t over 3. So that's 5 e to the 3t. Yeah, so the antiderivative of sine 4t is what? Antiderivative.
Minus 1/4 cosine 4t.
Yeah, 1/4 or sine, or 1/4. Is it cosine? Positive 1/4? Right. Okay, so derivative or multiplying, antiderivative dividing. Okay. Plus, yeah, call that constant 1 because that gives us y prime. We'll have to integrate this again. to get y. So the antiderivative of 5e to the 3t minus 1/4 cosine. Where did that, what happened? I don't want that there. Oh, hey. Cosine 4t plus c1 dt.
5/3.
Okay, yeah, 5/3 e to the 3t.
Minus sine.
Minus
Over
1/16.
Sine of 4t. Yeah, what else do we need?
1/16.
Yeah, over 16 or 1/16 out here.
Plus CT1. Or
Yeah.
CT1.
C1 times t
Plus C.
plus C2, yeah. Okay, and that's our y of t. So general solutions just means it's very general. There's infinitely many solutions to this, right? Like I said, the initial conditions are what then comes in and makes those constants precise. Do y'all have any questions on that? All right, so initial value problems, and these, let's see, these, yeah, that's the last kind of exercise we have in 9.1. So 9.1 was just a very gentle introduction. So it's the same idea. We're going to find the function y. We'll have a constant initial condition used to find the constant. So we're going to integrate sine t plus cosine of 2t with respect to t. And get minus cosine t plus 1/2 sine 2t plus c. Okay. So then we're going to use the initial condition. So initial condition y of 0 equals to, so the t is our independent variable. So this initial condition is it's t comma y 0 comma 4. So we're evaluating that at 0, and it comes out to be 4.
Don't you have to solve for C then?
Yeah. Yeah, okay. All of this right here that we're evaluating comes out to 4. Is what I meant. So C equals 5. This is minus 1. Minus 1 plus C equals 4. So C equals to 5. So then y of t is minus cosine t plus 1/2 sine of 2t plus 5. Does that make sense? Yeah. I think it's pretty easy considering what we've been doing. All right, do y'all want to give number 7 a shot?
derivative from here to here. So you have 1 minus 1, and then 1 minus 2. No, because you missed that. That's what, yeah, that's supposed to be 4. And then that goes to 2.
Put a 4 there, but then when I copied it down, Rachel.
Did you get that?
Yes. Indeed, I did.
Well, there's two conditions.
Oh, yeah.
And then for you, yeah, it's just turn over work. I got an application for the job previously, but the work is going to be so show yeah, show the
Yeah, I'm doing my application.
Yeah.
I want to do Boulder. It was like, I already started. I don't know. What about you?
I'll be able to.
Why did you choose Boulder?
Because my brother made me love it.
Yeah, no, I hear you. And for just a school, it is a really nice school.
And yeah, everything. I knew it was like a good geology school, so that also.
I don't know. Yeah, I'm thinking mine. Yeah, okay.
Didn't really put a lot of thought into my moving down here. It was just like, oh, my brother lives in Colorado. Oh, see you. Okay. Boulder? Okay. Yeah, I'll apply. Got it. And I was like, alright, I guess I should write my resignation letter. And then I moved out here the day after my last year of school.
Wow.
People didn't even know I went to
I mean, you get tired of these guys. I mean, usually people that went to Colorado, they want to go out to like the mountains.
I love
Every single one of my bosses is on the East Coast, and I don't like to travel. But I was like, masking I've learned a lot from it. I gotta say there's some benefits to it.
Why am I stressed?
That's
Who cares if I go there to get my phone?
Yeah.
To get my groceries and get there 3 seconds earlier. It doesn't matter.
you gotta have managers. So much cheaper. You have to
I
have
still drive like a New Yorker out there, and that's like I did the other day.
It's hilarious because I never do it, but people get mad at me and like, I have to work.
I'm like a New Yorker. Passenger seat, I like the age
Like the lab-based physics
He was
just
like
making
very
it based on that.
tense. always on cars. So you make even like 33K. So it's just like this, like, it's just like, they're quicker. Oh, no. It's just like,
Sounds exciting, but it also sounds like dangerous.
you'd be annoyed that you're stuck in traffic. Of course, it's traffic. It's East Coast. So you get annoyed that people aren't going faster. Like, everyone wants to go faster. It's not like someone's avoiding you.
Yeah, well, you know, a little bit of that's coming here. The streets here are getting so busy.
I went super good out of this lane to get into the turn lane, to then go forward, to then cut into the lane, to then block the turn lane. Those are the turn lanes. So then I was just like, goes on the side, goes by.
Yeah, no. I gotta say something.
Like that's obnoxious.
Yeah.
Come on, just sit in the traffic and take it.
Oh, yeah. Things we got to do.
All right, well done. There's going to be probably one of those on the exam from 9-1. The last page, does anybody have any questions? I saw some people just going through the process of finding the antiderivatives and then using the initial conditions after the fact to solve. For the constants, that's okay as well, if that's how you want to do that. The last page is, oh man, cut that. Oh well. It's a more technical thing, but just in case you were wondering, as far as like the uniqueness and the existence of solutions, that's really beyond the scope of calculus to justify. So the ones, it's basically saying that the differential equations we see here in this chapter, they do have solutions, and the solutions that we're finding are the unique solutions. So we don't have to worry about them not being well behaved, as they say. So maybe not all that relevant, but worth pointing out.
You learned that in Calc 3 really different.
Yeah, differential equations. And even, honestly, I don't even think a differential equations class here anyways would go into the details for the proofs of the existence and uniqueness, because those are usually very difficult to prove. But if you take differential at university or something, they probably would have you do it.
You know, I can't argue with it because it's kind of like the culture.
Yeah.
It works.
Yeah.
You're there, you're going to become like that.
I don't think they have a New York accent.
No, I wouldn't say that either.
But then like if I start to
Does it come out?
oh yeah. Get New York
That's the tense.
Just like the hands pull out. Oh yeah. Really like to walk and over that.
That's beautiful. No, I like that. I support that. I think when people really get to the roots like that. Yeah, exactly.
Let's just say, you know.
When I heard about the cheap, I was like, wow.
That's the other thing.
Okay, so 9.3, we're looking at separable differential equations. And separable means we can separate either side of the equation so that we have the same variables on either side, respectively. So this is sort of the generic format. The form of the differential equations is here, where it says y prime of t equals to f of ty. But what we mean by f of ty is that it could be an expression or a function of t, it could be a function of y, or both. But the idea is that this f of ty is constructed such that we can separate those variables, from the t from the y, and then put the y on the side of y prime. Okay, so it's what we're looking at here when we separate these variables, this into this. Then we've got it separated to where we have our functions of y over here. Notice it's different because we have this y prime of t mixed with a function of y, whereas on the right-hand side we just have a function of t. So what we'll see is when we introduce the antiderivative here, what happens to the y prime of t? And what? Yeah, so well, think about the notation y prime of t. That means take the derivative of y with respect to t. And we want to integrate the right-hand side here, whatever this variable is, it's just t here, but it could be x or w or whatever. When we integrate this side with respect to t, we integrate this side with respect to t. So when we introduce the integral with respect to t over here, then these differentials cancel, and we've just got, let me erase that, and we just got this right here, your g of y. So that's our dy, g of y rather. So then over here we just get that function of y dy. On the left-hand side over here, we just get some function of t integrated with respect to t. So we're separating the equation so that we've got an integral over here involving one variable and an integral on the other side involving another variable. So that's what it's kind of looking at right here. And they explain that a little bit better, integrating both sides. Y prime of t dt, so that's our, sort of like our independent variable here, dt. This cancels that y prime out, so we just end up with integral of gy and integral of h of t. Does that make sense? When we look at the first couple of examples, I'll write that out, but and when you see these here, the y prime of t is just as it is. The things that are different are what this g of y is and what this h of t is. So this y prime of t, whatever it is, y prime of t, y prime of x, y prime of s, all of those stay as is. So that's exactly how we'll see them in the differential equation. So for example, y prime of t equals to y times x squared plus 1. That y prime of x is just going to sit there as it is. We're going to leave it alone. But we do want to separate the variables over here because we have y and x. We want to put this y on this side with this y. So we're separating those variables, leaving the x's on one side and the y on the other side. So we'll have 1 over y times y prime of x equals to x squared plus 1. So that we've separated that, and then we can integrate both sides with respect to our variable x. So just to save some space, we're going to now separate and then integrate with respect to x. I'm going to have to write smaller. Is everybody okay with that? Anyone have any questions? Yeah.
Just to clarify, then that is y times x squared plus 1, not y of x squared plus 1.
Right, yeah, y times x squared plus 1, right. Yep. Okay, so here's where the y prime goes away, because this y prime, we're going to write this as, or think about this as dy over dx. And so that dx and that dx cancel. So we just end up with the left-hand side integral of 1 over y dy equaling the integral of x squared plus 1. Remember, the goal of a differential equation is to find the function y so that the derivative of the function is the function itself times x squared plus 1. That's what we're after. Okay, so antiderivative of 1 over y. Yeah, so ln absolute value y. Normally we would get a constant here. I mean, I suppose we'd still do, but we're just going to keep the constants over here on this side. And then the antiderivative here, x cubed over 3 plus x plus c.
Did you just multiply E both sides?
Yeah, yeah, exactly.
So basically both C's are just on the right-hand side as well.
Yeah, exactly. Oh, okay, well, that failed. It's really hard to tell when I type these out in Word how they're going to translate to the smartboard. I leave myself enough room. Yeah, so we want to solve for y, so we exponentiate or raise both sides as the power of e. So we're going to have e to the ln absolute y equals e to all of this stuff. Let's just say here, the absolute value of y is e to the all of that stuff.
Or we can put C up there too.
Yeah, we're gonna not put it up there in a minute, but it is up there. The way we're gonna handle that is we're gonna look at it as e to the this times e to the c, right?
Just say that's just C.
And then we just call that another constant. E to the c is just another constant. So we'll call this, maybe I have space, I'm not sure. So that's e to the x cubed over 3 plus x times e to the c.
So you just put that C up front, right?
Yeah, so, but e to the c gets absorbed as another constant. So call that a or b or c2 or whatever you want to call it. So we're going to call that c1. Yeah.
So is there something wrong with leaving it as natural log of absolute value of y, that first function?
No, you can leave these as implicit solutions. We'll look at one example towards the end. But generally, solving for y, if and when we can, we do. Just so it's an explicit solution, not an implicit. And the instructions will be clear. If they want you to leave your answer as implicit, like ln of y equals 2, then it would say, leave your answer as an implicit form. Okay, absolute value of y is sort of redundant now at this point because this right here is positive. So we could just say that y is that constant times e to that power. I can fit that here. Now hopefully that shows up a little better in your notes.
And the constant does need that subscript 1.
It doesn't really matter. I mean, if we would have chose our constant up here to be C1, then we could just call that C. You could call it A or K or whatever. My math lab would say like use C1, C2, C3, etc. for constants. So I think as long as you type in C or C1 or C2, it'll be okay in the homework. Any questions on that example?
That's it?
Hmm?
That's the whole thing?
Yeah, we found Y. There's Y.
Okay.
So you know, if we wanted to check that, we know that the derivative of Y is Y times X squared plus 1. So then we could go back to 9.1 and say verify that this is a solution, right? And we said, well, Y of X really is this constant times this thing. Okay. Yeah, okay. So the derivative, then we just find the derivative of this function. So find Y prime. And then multiply it by this right here. You should get that right there. Y times, Y prime rather should equal this times X squared plus 1, my bad. So then all of this right here should equal all of this. And that's how we could check our solutions that way. Okay. So how, example 2 then, U prime, how would we separate that?
Probably through natural log of each side.
So the natural log of both sides, then we would have just 2x minus u equals u prime, and then we could add u to both sides. So then we would have this. If we introduce the natural log here, making sure, we would have ln of u prime plus u equals to 2x, right? There's nothing algebraically wrong with that, but then we have to do this, right? So we integrate both sides with respect to x over here. Do we want to, is that something we want to look forward to doing? No, I mean, we've seen how do we find the antiderivative of the natural log of something? Well, no, like this here. What if we just had this here? What do we use to find the antiderivative?
Integration by parts.
Yeah, integration by parts. Well, what if we wrote u prime of x as e to the 2x times e to the negative u? In other words, u prime of x is e to the 2x over e to the u. Can we separate that?
How should you, how do you do that? Oh, I see.
Yeah, you can separate the e to the u multiplies both sides. So then we have e to the u times u prime of x equals e to the 2x. So you know, there's weird notation just because it's like, you know, you see like u prime or w prime of s, you know, like it's just weird notation, but basically we're trying to get the function with a variable to match the derivative on one side, and then the other variable that the derivative is a function of all by itself over here, right? So e to the u prime, right? Function of y with y prime. So that's just how it goes. And then so from here, once we've separated it, then we'll integrate both sides with respect to x. So we have the integral of e to the u du equals the integral of e to the 2x dx. So integrate both sides with respect to x. Keeping in mind again, u prime is du over dx. So those dx's on this side go away. We just have du. So we have left-hand side e to the u, right-hand side is 1/2 e to the 2x plus c. And what are we after? U, right? We were given that u prime. We want u as a function of x. Yeah, so now we'll use the natural log of both sides. That's it, there's u of x. I mean, I know we're writing u, but it's, you know, it's like writing y equals to 2x. It's still a function of x. Do y'all have any questions on the process here?
Or just like the process as you get to
Do what?
taking the,
Sorry, say that again?
instead of like the process of like taking the, before you get to what taking the.
Either or. Okay, so these can have initial conditions as well, or initial values. So I think one of the biggest thing with differential equations, if you take the course, it's pretty algorithmic. If you have this kind of differential equation, then you do this. If you have this, then you do this. It's pretty sequential in that sense. I think it's just hard to get used to the notation at first, because they do use different notation than we're accustomed to seeing in like algebra and calculus. But here we've got 2 times a function times its derivative equals to 3t squared with y of 0 equal to 9. Now keep in mind that this initial condition or initial value, the function is a function of t. So t is your independent variable and 9 is the result, or 9 is y. So this is really the point 0, 9, where that's x, t, is what all of the points in that plane represent, x, t. Sorry, t, comma, y. So this is y right here, and our independent variable is t. My bad. I just totally messed that up. So then we would look at, the ty coordinate system. And again, these initial conditions or these initial values are the things that help us find the constant. Well, some of these have, you'll see they'll have like really weird solutions. In fact, 1 or 2 examples in your homework has you graph these. And so you see like infinitely many solutions. And that's when you kind of default back to the initial condition to tell you, well, which one of these is my solution? Is it this curve over here? Is it this curve over here? It could be all of them, but then you have an initial condition and you have to say which curve actually passes through this point. And that's how you determine which part is your solution. Okay, so separate that or no? All right, yeah, it's already separated. We've got our derivative with the function y over here, and then the t on the other side. So this is already separated for us. So we're going to then just integrate with respect, both sides with respect to our independent variable t. So the integral with respect to t on both sides gives us 2y dy, and the integral of 3t squared dt. And then so that gives us y squared equals to t cubed plus c.
So why wouldn't you add the c to the other side too?
We would have, so we would have, let's call this, we would have this scenario here,
Yeah.
like that. And then so we'll just subtract this constant to this one and call it constant. Nope, that was fine. So we could just use the initial conditions here, or we could keep going a little bit and say y is equal to the positive and negative square root of t cubed plus c. Doesn't really matter. Once we have an expression for y in terms of t, you can plug your initial or your values in at that point. So we have y, and now the initial condition or the initial value is going to help us determine which one of these curves it actually is, right? Because you got two curves. It's probably helpful to think of this as y of t if you need to. But here, let's plug in our initial conditions or initial values. And so we have y of 0. Which is equal to 9. So just based off the initial condition, which square root is it?
The positive square root?
It's the positive because y is positive, right? Y is positive 9. If it were negative 9, we would take the negative square root. Okay, so what is c equal to? 81, yeah, because we've got the square root of c is 9, which means c is 81. And so our y is the square root of t cubed plus 81. And I'll just note here positive because of the initial condition. Y is positive. So the solution says that if we look at the original differential equation, if we take 2 times that function and multiply it by its derivative, then that will give us 3t squared. That's what that says. All right. Any questions on that? So why don't you try example 4?
Just simplify that to y equals t squared plus 9.
T squared plus 9 under just by itself?
Yeah.
No, you have the sum of cubes right there. Let's think about it. 3 times 3. No, you couldn't even factor it as a sum of cubes. So, yeah, you got to leave it as it is.
E to the 0 would be 1, right? So 1 times E to the C. Yeah, I can do. So wouldn't it be 1 times E to the C?
So I started off that way, and then I was confused, so I just left it as that, and then I just did ln of 3 with the sine of 0 plus c.
Ln of 3.
I don't know if that's no, because then that just got rid of the e, and then I just made it ln of 3. So I can just see.
Oh, for the,
It's only.
oh, right, okay. I see.
Because I didn't do that before, but then I was.
Not supposed to. Yep.
No,
You got
and
two.
e to the c. Yeah.
But they both work. Needed the same, right? Because this works.
Yes.
I totally get what you did here. One was.
Yeah, they both work, because then if you do it the other way.
Negative sign. Is this the integral cosine should be the sine, just the derivative of sine? Oh, right, okay, sorry, I was thinking derivative.
And then it's just
That could be this stuff.
3 minus
I'll do like the
one.
one of those giant
on
problems.
C, so then ln. Then when is the ln?
But you can't. You finally click. So then you have to.
Oh, but it would be ln of c. It would be ln of sine 0.
It's like trying to use substitution, it takes so long, and then I just started using matrix instead.
That's why I'm confused, is because I feel like
They both work.
they both work.
Which is just
Shows that
Which is, yeah. Right, ln of sine of 0.
Sine of 0 is 0, then e is 0.
What's ln of 0?
Ln of 0.
Is that 0? What?
domain error.
No, it's Ellen.
How'd you get this? Because you're equal sign of 0 plus. It has to multiply.
Oh, that's very high.
So then that would be 1 times e to the c. But that's what's so confusing, is that that would just be e to the c, right? But then the way you did it also makes sense to me. But then that would get you this here. So what'd you get?
That's where you are.
It's got the C inside X.
The c.
We don't know.
So that is
I was
constant.
Yeah, that's what he did in the first
issue. I have an artist.
You see it's turned
I don't know, this might make sense to me, but I don't know if that's legal.
That's what I think. That's what it could be.
Oh, what sine of 0 is 0?
Right, so then 0.
Yeah, e to the power of 0 plus
Oh, that's weird. Here we go. Back to the I like to bring it. Makes it seem like that.
This is the New York race.
Oh my God. That's why. E to the C, where C is ln of 3 is 3.
Yeah, so
So ln of 3 is correct, but you got 3 of this. Because it's 2 different.
ln of 3 is 6.
Okay, so
Or
It's just a B.
I forgot I didn't know that.
Yeah.
Okay, so the constant's actually.
That's what I think it's
Right.
Oh, okay.
Oh, good, that makes sense. Yeah, so get it there, otherwise we're missing there. Right.
Because like I get both ways and I don't know which.
It's either is right.
Want to see the stupidest pen I've ever heard?
Because it depends on where you determine your constant, right?
Yeah.
So it's just about
This is for like elementary school, so that you have independentship.
This is 3, but that's e to the sine plus c.
Oh, from an ear. There you go.
There we go. I was like, wow. Okay, that's pretty So, can I ask you a question?
Yeah.
So would you, I mean, my argument, I was gonna do L on both sides to isolate my C, but we could just say this is C.
Yeah, exactly.
So C could be 3 or L and
I'll write it down.
I feel like those are different numbers.
They are, but in the sense of the original function, e to the sine plus c. I think they put like yeah. Or if it's L here, y, 40 to y.
So either answer is right.
So like if you left it exactly.
C times 1
If you left it like that, and you said that C is ln of 3, and that's it. But we want to solve for y, so then you have this, and you have this, and then e to the ln of 3, right, times e to the ln of 3. That makes that 3.
Alright, I don't feel so dumb.
No,
So then the answer is 3.
3 equals C times e to the sine of 0.
So this one, I have
Equals C times 1.
that.
C
They're
both right.
How it can be sine x is e to the c.
The whole VR stuff in general is like slowed down. It was super big when someone finally made it. And then like no one was It's like I didn't think there was 0, 0. Otherwise, you're going to get every time you was like, all right, so that's the thing about very fast and get away from I think it's $700 on top of like every calculation you on right?
It's killing me.
The mountains, everything.
I feel like some of the engineers like
I gotta remember that phrase one side to ln or to e and e to the negative raise the entire side.
You know that.
I totally forgot that.
it's just
I'd say like at least like $800.
I used to only drive like 40 minutes and I was
To be able to run it, it's ridiculous. It's so much money to do it for something that's like
You don't go, you want to be by the water.
I'm much more of like a sit.
I think they call that a task. Yeah. Yeah, when you're diving and you like work out, not only do you have to like on the shelves where and you just think there's everything like
All right, most everybody got the right answer. There was a little bit of, I wouldn't say a discrepancy, but some people had their constant as ln of e, and some people had their constant as 3. So the idea is that
if I've got ln of y, I can still use this y is 3 when x is 0 initial condition. So let's just say here, if I plug in the initial condition here, I have the ln of y when x is 0. Right, so then what this tells me is that my constant is the natural log of 3, but I haven't solved for y. That came from the implicit form. So let's just say this is, 1. What I would have to do here is say then the ln absolute y is equal to sine x plus ln of 3, right? And then continue to solve for my function y. Oops.
That would just be y.
Oh yeah. And then we write this as e to the sine x times e to the ln of 3, and that's just 3 times e to the sine x plus y.
Yeah. So the top one is the implicit form, so that would
Right.
be correct if that's what it was asked for.
Right, yeah.
And then the bottom one is called what? Just
This is actually the solution.
That's the solution.
Yeah, implicit. And really the implicit form is here. This is the implicit form as a specific thing. That's the general implicit form.
Explicit, though, would be y equals e to the sine of x plus c. Or I
Yes,
guess-
right. So notice if we took the implicit form in equation 1, we'll call that equation 1. Notice if we take that instead and solve for y and then plug in the initial conditions, then we have the same solution. So we have, what was that? E to the, sine x plus c. And then we solve for y and say that's e to the sine x to the power sine x plus c. Then we plug in our initial condition. And then this is when we'll get the solution c equals 3. So we have y is equal to 3 when x is 0. And we'll write this as e to the sine x times e to the c, which is, some constant times e to the sine x. So really we could have started with this as well as e to the sine x plus c power. It doesn't really matter. You get there either way. So a to the e sine of 0. So and of course what that tells us is 1 times a is equal to 3. So y is equal to a e to the sine x or 3 e to the sine x. Either way you look at it, but you want to make sure that you are actually explicitly stating the solution. Any questions on that? Yeah.
Would you count it wrong if on an exam we wrote it as e to the sine x plus ln 3 all in the exponent instead of pulling that 3 out?
Yeah, so this thing right here, that's okay. You've basically got the solution. It doesn't really matter all that much saying it's 3e to the sine x or sine e to the sine plus ln 3. It's really the same thing. I think as a general practice, just making it as simple as possible is a good rule of thumb. But honestly, like if you're programming this, the computer doesn't care if it's 3 e to the sine x or e to the sine x plus ln 3. It computes it all the same. It's the same computational time to compute that.
The homework for the partial fraction seems to be pretty
Picky.
about getting into really reduced log.
Yeah, especially when in the partial fraction section when we have ln of the square root of x squared plus 9 over 2, what is it, plus x over 2, they really want you to take care of that 1/2.
What I mean is they'll have, a bunch of different ln's and then, ln.
Oh, a
plus
single
plus.
logarithm.
Yeah, and they'll
I
have
see.
you put it into like multiplying within a single argument.
Yeah. Yeah, I'm not as picky as my math lab. So if you want to, and I know it's hard to maintain consistency, right? Because my math lab expects a certain standard from you, and then when you take the test, I say, write it either way. It doesn't matter. If that's confusing or inconsistent, because it is inconsistent, right? I just feel like I should be a little bit more lenient than the computer, just because I can. But if that's if that's a big deal to you, then just do the exam problems like you do the homework problems. Okay, I think it's a good spot to stop. We'll look at solutions in implicit form and then wrap this section up after break.
It's like 200.
Y'all ready? So the instructions here do say to leave the solution in implicit form and use the graphing software to plot the solution. So here, clearly you're going to use technology to plot the solution. So this shows up, as one of those -T problems in your homework. And be sure to indicate which function corresponds to the solution. They'll give you multiple choices. Which choice is actually the solution is what you're looking for. Okay. So our first step here should be to do what?
Multiply sine the other side.
Yeah. So we've got 1 over sine and cosecant. So we'll multiply that over here. We have the sine of u times u prime of x equals to the cosine of x over 2. Now, keep in mind that if we're looking at this, our original differential equation as 1 over sine u cosine of x over 2, there's some things u can't be.
0.
Yeah, u can't be 0. And then we know there's multiple or infinite instances where the sign is also 0. But this is where we can kind of use our initial condition to narrow that down, right? The initial condition is the point what? What's the point here for our initial condition?
Pi over 2.
Yeah, pi over 2. And again, that's our independent is x. Our dependent is u. So we could say, sine of u is 0 when u is 0, when u is pi, 2 pi, et cetera, but do we need to go out that far? Do we need to consider pi and 2 pi and all of those other ones? No, because our initial condition has u ending at pi over 2, right? So, or it's not ending at pi over 2. It's just that that's where that particular point is as a solution to this differential equation. Okay, so u can't equal 0. We'll remember that as we chug along. And we're going to integrate both sides with respect to x. And remember again here, u prime is really du over dx. So the integral on the left is just the integral of sine u with respect to u equals the integral cosine x over 2. dx. So then antiderivatives here will give us our implicit solution. Negative cosine of u equals to, what's the antiderivative of cosine of x over 2?
2 sine x over 2.
Right. So leave the solution in implicit form. So when we find c, we're just going to plug c back into this implicit form here. What was it? Pi over 2. Initial condition. We have minus cosine of u was pi over 2. I don't know if that's measurable. And x was pi.
Nice, we're good.
So what does c equal? Yeah, so we've got 0 on this side. 2 sine of pi over 2 gives us, sine of pi over 2 is 1 times 2 plus c. C is negative 2.
No, C is plus. Right?
Well, no, because it's 0 equals 2 plus c, so c has to be negative 2, so that's 0. So the implicit solution is negative cosine of u equals to 2 sine pi over 2 minus 2.
Could C also be 2 though if you multiply negative cosine?
Yeah,
by 2?
yeah. Then you would want to say cosine of u is minus 2 sine of pi over 2 plus 2.
Pi over 2 or x over 2?
Oh, is it? Yeah, it was x over 2. Yeah. Is that what you're going to say, Ryan?
I was gonna ask, so then would u of x be negative inverse cosine of all of that on the right side?
You pull the u out.
Yeah, close. It's the inverse cosine of the negative of this stuff. Yeah. So we would negate first and then inverse cosine. So this one's not terribly hard to solve for you. You know, let's also look at that. That's not what the instructions ask, but we could say that u is the inverse cosine of negative 2 sine x over 2 plus 2. Yeah.
So can you just give me a good definition of what implicit form defines?
So yeah, explicit. So let's talk about what explicit is. Explicit is when we explicitly state what this function is in terms of another variable. Y equals to x squared plus 1. Y equals to cosine of x e to the x. Those are explicit. Implicit is when it's implied what the function is in terms of the other variable. So here's implicit. It's implied what u is in terms of the variable x. This is explicit. So you remember implicit differentiation? Where we were finding the derivatives of, things like this, something like that. we didn't have to explicitly solve for y before we took the derivative. We found it via implicit differentiation, where it was implied that y was some function of x, although sometimes we couldn't solve those equations explicitly for y. Sometimes with these equations, you can't explicitly solve for u or for y or w or whatever, so. All right, let's go ahead and look at the graph, and then maybe we should talk about the condition where u can't be 0, because that's going to help us with determining what our actual solutions are, or is. Okay, so, which solution is ours? Which part are we after?
The one that goes through pi over 2.
Yeah, the one that goes through the point pi over 2. So let's plot that. There's our point. But I can't remember if this one was in your homework or not. I think you had 2 like this. But the idea is, sorry, if you look at the instance where u can't be 0 in that implicit solution, negative cosine u, etc., that's going to give us certain values of x. Okay, so we'll put that in our notes, keep that in mind. This one we happen to be able to look at it explicitly too, so let's put our implicit solution in, and then we'll put our explicit solution in. We'll put this in down here. This will be for So notice this is only giving us the half of those ellipses. It's not giving us all of those other ones, right? Let me do this. Okay, well, let me turn this off. Okay, see that they do confer with one another, but only for certain values. Right, there's our implicit solution, there's the explicit solution.
So explicit just allows for more, or for more specificity.
Yeah, and if we think about it, why would it be more specific here with the arc cosine of all of this versus the negative cosine of y equals to all of this?
The domain?
Because of the domain of what? Yeah, the domain of inverse cosine, and also not just the domain. Here's the domain we're seeing here, these pieces. But in the implicit solution, we also saw we had the other above and all of the ellipses above and below. Also, the range of the inverse cosine is restricted from 0 to pi, right? So we're seeing the domain restriction here with these pieces, and we're seeing the range restrictions. That's why we don't get all of these other ones up here or down here. So looking at the explicit solution, sometimes we can look at it, sometimes we can't, right? If we can solve for u here pretty easily, other times you can't. But the idea is that this piece right here is the one that passes through our initial point. So it's really this piece right here that's the solution. But what happens here at these 2 points? Because at those 2 points, u is equal to 0, right?
Must be always.
Yeah, and we said u can't be 0. So that's when we could go back to the restriction that u couldn't be 0 and say, well, you know, really all of these things are holes right here.
Well, we can't see.
You just can't see them. And Desmos doesn't, you can't hover your mouse over any one of these points on an implicit curve. It won't define them. You could define them other ways, but so really all of those are holes when u is equal to 0. So without the graph, the way we figure out that's the part of the solution that we need is we just go back to the implicit solution and say, well, when u is 0, what happens? So we let u be 0 and then we solve for x. Remember, this u can't be 0 came from the original differential equation. We clearly see that u can be 0 in the solution, but we're looking at the original differential equation and saying, all right, well, then what happens when u is 0? Well, I guess we don't need this here. When u is 0, we've got the cosine of 0, which is 1. So we have negative 1 equals to 2 sine x over 2 minus 2, which means that sine of x over 2 would be what, 1/2? No, wait. Yeah. Okay, when's the sine of something 1/2?
When it is pi over 6.
Okay, pi over 6 and
Now we're gonna multiply both sides by 2, so it'll be pi over 3.
okay, but where else is sine of what something equal to 1/2?
Oh.
5 pi over 6?
Yeah, 5 pi over 6. So that occurs when x is pi over 3 and when x is 5 pi over 3. So really we're saying that the solution is valid. The implicit solution is valid as long as x is in between those two values. Right? X can't be those two values because those two values were when u was 0, u can't be 0. Okay, basically that gives us the point u was 0, x is pi over 3, and 5 pi over 3, u is 0.
Oh, we have to do this on the test?
No. So the implicit curve is not defined at those values. And so when we go back to, the solution, here, we can say, well, here's the point 0 pi over 3. This is 0 pi over, pi over 3, 0 rather. And this point right here is 5 pi over 3, 0. So So those implicit solutions, those ellipses here, they're all broken up. They're really two pieces, right? It's the top half and the bottom half. You don't see that by plotting the implicit solution, but we can clearly see that with the explicit solution. But again, not all the time can you solve explicitly for something. So we have to rely on analyzing the implicit curve to determine, okay, well, if you can't be this, where does x have to be? X has to be between pi over 3 and 5 pi over 3, not including, and it has to pass through that initial point. Yeah.
So, because there's two semicircles, is there a reason why it's undefined at those points? Because there's really a gap in between where the ellipses meet, I guess?
Yeah, so this is our implicit solution is really like this, with our deleted points right there, or holes right there. So they're really two different, this is like some part of that function, this is the other part of that function.
Makes sense.
But then when we come in here and say, well, that's the inverse cosine, the domain and the range get affected now. So that's what we're seeing here with just the top half, is the affected domain and range due to the inverse cosine. Okay, so the solution we would just say is, we pick this particular graph, but the graphs have descriptions underneath them. So it says the solution is the entire ellipse, the solution is the bottom half of the ellipse, or the solution is the top half of the ellipse. So really, you get the graphs, but you have to pick which description is accurate. So just heads up on that. We could find an implicit solution like this on the exam and just be done with it, right? You wouldn't have to graph it. And honestly, we could get through determining the solution, at least where the solution is, without graphing it, right? Because pretend we didn't have the graphs. This work right here tells us that our implicit solution is valid for x between those two values. So negative cosine u equals to 2 sine x over 2 minus 2 for x in between these two values. And then that's really all we could do without a graph. But I don't think I would honestly have you go that far with something on the exam. There's enough to worry about.
Good.
Or to think about. Maybe you worry about it or not, I don't know. All right, any questions on that section? Yeah, they could be really difficult too, though, right?
Yeah, separated out.
Yeah.
The 9.1 stuff. Yeah, we're gonna have this chance. I think that's how it's done. Well, in the sense where at least we have something for your class. If you want to be the top student.
So the questions, content of the second exam, we're going to have 5 to 6 basic antiderivatives. And those particularly could fall into the category from 8.1, where we were using some basic integration techniques, multiplying by a form of 1, those kinds of things. 8.1 and honestly, you should know all the derivatives of, the antiderivatives of all 6 trig functions. So antiderivative of secant, those other ones that we looked at, I believe, and 7.3. Or sorry, 8.3. I'm still used to the old textbook. 8.3. So 5 or 6 basic ones.
Are you gonna put this?
Yeah, D2L. Yeah, I'll upload this. There'll be 2 questions regarding integration by parts. From 8.2. And you should honestly be familiar with both the indefinite integral and the definite integral.
To be able to do both of them, is what you're saying?
Yeah.
Okay.
There will be 2 trig integrals. From 8.3. And outside of the ones that are like integral of secant, integral of cotangent, outside of those, particularly what I'm thinking of here is the powers of sine and cosine. And the powers of secant and tangent.
Does that include the power reduction rules?
No, you don't need to know the power reduction. In fact, the ones I have on the exam, I'll try to remember to put in the instructions, do not use power reduction formulas. So if you use the power reduction formulas, if you memorize those, kudos, but you will not get points if you use them. So we specifically want to be familiar with the procedure in either one of these cases. M and N determines what we split off. That determines our U substitution. So remember, these integrals like this are really just U substitution in disguise. It really depends on, what you split off is really the heart of what the integration entails. Okay, there'll be 2 questions regarding trig substitution. What was that, 8.4? There'd be 2 to 3 questions for partial fraction decomposition. In 8.5. And I probably just have 2 actual integral questions. One of these questions will be setup only. Setup only.
I'm guessing like we have to solve for A, B, C, D.
Not even solve for A, B, C, D. What I mean is, for example,
Yeah, like A over.
yeah,
Yeah.
if we had 8x over x cubed times x plus 1 squared times x squared plus 1 squared. Like set that partial fraction up, A, B, C, D, etc. But so that'll probably be one of those. The 2 other ones will be actual antiderivatives. I know this is sort of vague, but I do what I can. Okay. And there will be 2 improper integrals. From 8.9. Let's see. And then also one question each from 9.1 and 9.3. So one question for 9.1. In 9.1, I will have you solve initial value problems, those last few examples in 9.1. So one question where you solve an initial value problem given, y prime of x or whatever, y double prime of x. From 9.1. And then one question, solve separable differential equation from 9.3.
It's like 20 questions. Doesn't seem like that many questions.
Yeah, I mean, some of the procedures are sort of lengthy, I think, and I just have to allot for everyone to be able to finish.
There's a lot of parts.
Yeah, right. And if you finish early, bonus.
Hey. You mean read over your test and make sure you know.
Yeah, always a good idea. Okay, so that's it. That's the content of the exam. Questions y'all have? Do y'all have any questions? I'm devolving into a Neanderthal.
So you actually wrote an example for partial fractions setup only. Can you just show up the setup for that one?
Sure. Yeah, it's going to be pretty long. So we've got so I can fit it. Maybe I can fit it here. We've got x cubed. What kind of factor is that? A repeated linear, right? It's x minus 0 cubed. So that's going to look like what?
A over x plus b over x squared.
Yeah.
Plus c over x cubed.
Okay. How about the x plus 1 squared?
Plus, it'd just be plus d over x plus 1 and then e over x plus 1 squared.
Yep. Or maybe it won't take a... Okay, and then the x squared plus 1 squared.
F over x.
Okay, remember though, it's over irreducible quadratic, so we've got what over x squared plus 1?
X plus b.
Yeah. So that has to be a linear f times x plus g. Then what?
Plus gx plus
Use some different letters here. Over.
X squared plus 1 squared.
Right. X squared plus 1 quantity squared.
That's as far as we have to go right there?
Yeah.
Oh, okay.
Yeah.
Otherwise, you'd multiply it all by 9.
Otherwise, something like that, you end up solving those with matrices. I mean, you can solve them like systems, but you have to eliminate so many times. It's easier just to put it into a matrix and solve. So, time consuming, not on the exam, other than just the setup. If you were taking Calc 2 at a university, they probably honestly would put a question like that on the exam.
You'd have to solve it.
Yeah. They don't care. They just say, hey, test on Tuesday, see ya. That was my experience anyways. Hopefully it's not yours.
I appreciate my friends.
Do they expect you to solve it like without knowing how to use matrices?
I guess they don't really care as long as you solve it. Solve it. Yeah. Okay. Any other questions or area of difficulties y'all are having?
We have review on Tuesday.
Yeah.
This is review, right?
Yeah, this is the
Currently in
review.
it.
Yep, test on Tuesday.
That's not.
I probably should have mentioned that. Oh well. We're all hopefully responsible.
Yeah.
I hope anyways at this point in your academic careers I feel like other classes, I do have to remind them, hey, you got a test coming up. I'm not so much worried about y'all, but hey, we got a test next class period.
I know.
All right, well, I'll stay, but you're free to go. If you have any questions this weekend, I'll be on and off. My phone's, or my computer's messed up at home, but I can still respond through the phone, which might be a little clunky if I have to do math, but I can certainly, I still have access, so please email me this weekend if you have questions.
And you fixed the quiz due date?
I did,
Okay.
yeah.
I saw your email.
Yeah, and actually,
Nice to check.
yeah, thank you.
And there was actually a few
All
of
of them were
Okay.
like that. So I'm glad you pointed that out. We had like two co-leads, myself and some other person, working on putting the assignments in there before the semester. So it was a bit.
Because I went to look at it, it was like past due. I'm like, no, it's not due, it's not past due.
Yeah, I appreciate that. Somebody would have caught it sooner or later, but thank you. Sometimes people catch stuff like that and don't.
And we all get 100.
Yeah, that's the rationale, right?
I was that mean teacher that was like, or you all get zeros because none of you were responsible enough to talk to me.
Yeah, that was right.
That was,
Yeah, the test of that.
you all failed. Middle schoolers, I should have known better.
Thanks, you too.
I'm also going to these other lectures. This guy, his name is Professor Leonard. He does really good at
That's what I'm saying. It's so super easy for me to get that.
and it's literally just him. I think he works at college.
I still haven't-
Just him and like 5 hours from that class. Yeah. I give him the whole lecture. Like they just finish the whole right now.
This, like, I get this.
I do have 2 hour video of
Do you know John?
pulleys and
I was gonna ask you
and
because
shit
if you
like
did,
that.
I might.
It's like 2.5 hours.
Ask you.
It's gotta sit for that
Sounds
whole
like
thing
so much better.
next week.
No idea what the job it is.
That is fine.
It's coffee, right?
Are you working this weekend? What's that?
I said it's coffee, right?
No, yeah. Working? Yeah. So.
Random question, are you gonna have the circle on the board again?
I won't. If the other class has it, I won't erase it.
I'm down to man.
Because
Will they?
I'm gonna try to schedule for
I don't know.
tonight.
You can sneak in
If I
early.
remember to, it might just have to be
Put it on there.
If not,
I don't know if they
just
came
let me
from the
know
other
if
class or not.
If you guys are meeting up. But I'll just let you know when my work schedule is, if I can meet up with you guys, I'd definitely be great. You too. Well, I'll see you at least on Monday then.
Wait, 3 was the one that you had the trouble with, or you got 3?